Welcome to this UK Catalysis Hub webinar. It's my very great pleasure to introduce Dr. Rosa Arrigo from University of Salford, who's going to talk about catalysis by carbon-supported metal species. Over to you, Rosa.
Thank you very much, Josie. So good afternoon, everyone. Thank you very much for the nice introduction and for having me here today, talking about carbon-supported metal species in catalysis. And I would like to discuss the understanding we have developed in my group on the reactivity of this metal on carbon system by applying an approach, a research approach, which, if you want, can be considered mainstream nowadays and goes behind the trial and error approach of synthesis and testing to produce more robust structure function relationship that can hide that will enable the catalysis by design. And this approach involves the structural characterization of operando materials, so the structure under operando condition that the catalyst assume. And so I will be showing data on, so I will be showing a lot of spectra. So we apply X-ray spectroscopy, X-ray absorption spectroscopy, including photon out electron absorption spectroscopy, which is intrinsically bulk sensitive and provide information about the electronic structure of the materials, so oxidation state, coordination geometry, nature of ligands, and so on. We apply these in an ex situ fashion as well as in situ fashion to study the dynamics. But I consider myself more of a software X-ray spectroscopy, and particularly I've been developing methodologies to study materials in situ by using electron detection techniques. Due to the characteristic of electron detection, these techniques are more sensitive to the interface, which is relevant for catalysis and electrocatalysis. So I will show you X-ray absorption spectroscopy based on Auger electron yield or total electron yield, as well as X-ray photoelectron spectroscopy. You probably are familiar with this. It allows quantitative elemental analysis, compositional depth profiling, as well as understanding the environment of the scattering atom, which is complementary to X-ray absorption spectroscopy. Not only spectroscopy, but also microscopy. You will see a lot of electron microscopy images, which we use to, in combination with spectroscopy, to understand these materials. Now, going to the chemistry of carbon, in this presentation, I'm going to talk about the support effect and how this influences the reactivity of metal species, as said in my title, and particularly a common thread in my research from very early was understanding the nitrogen, the role of nitrogen in this metal support effect. Now, if you consider nitrogen doping of graphite, and you look at the electronic structure of graphite. Graphite is a semi-metal or a zero-gap semiconductor, if you want, and at the K point is the point where the valence band and the conduction band meet. Now, if we introduce substitutional doping and we break this symmetry, a gap open up that you can see here, and depending whether the atoms has an additional electron compared to the carbon, like in the case of nitrogen, or as an electron less, like boron, we can have localized states above or below the Fermi level. And we have semiconducting properties. Now, of course, in electrocatalysis, for example, this is an important aspect. But from a chemical viewpoint, you can consider that these localized sites can react with the solvent or with the reagent. They can be protonated, so they can manifest acid-base properties, which can be exploited in catalysis. Also, you can imagine this site being anchoring site for metal species, and thereby enhancing the stability of this metal species via metal support interaction. However, I will show you in the next couple of slides that the effect of this treatment, of this functionalization of carbon, will influence the surface chemistry, which manifested the nanoscale like I just described now, but actually also influence mesoscale property, because one has to consider that the degree of functionalization as well as the type of functional group will change the extent of the hydrophilic domains of graphite, of the surface of graphite, or carbon materials, graphitic carbon materials in general. And this, of course, will have an influence in the very process of preparing a catalyst by, for example, top-down approach with the immobilization of metal species on this carbon support. The very first example I want to start with is the use of nitrogen functionalized support for immobilizing colloidal palladium nanoparticles and their application in selective oxidation. And now you can see in this slide that here I'm reporting and this is the selective oxidation of benzyl alcohol to benzaldehyde. Now, as you can see, is that the surface chemistry of the starting carbon nanotube support has a strong influence on the reactivity of this palladium nanoparticle immobilized on top of it. Particularly, we see that the nitrogen functionalization, post-functionalization of the support at 873 Kelvin has a beneficial effect if compared with the same treatment at 673, 473, and the oxidize of the starting materials. Now, why is that? What we have observed is that the palladium nanoparticle immobilized on this carbon support actually are smaller if compared to the starting colloids, and they are also embedded here, you can see very well, on the carbon support. So as a way, and this indicates a stronger support interaction, whereas, for example, in this material here, palladium on nitrogen functionalized at 473 Kelvin, they remain, in terms of size, they remain the same as in the starting colloids, and they are not very well wetting the surface, so a weaker interaction. It also, this support here, which is more hydrophilic than the 873 system, is actually also loading less. So here I'm showing an example in which the diffusive or interaction, dispersive interaction between the support and the colloid at the beginning of the immobilization play also a role in determining the final properties of the materials. Now, of course, intuitively, we are thinking of the nitrogen speciation, and so we are looking at it by means of XPS. XPS is a quite routine technique applied to understand the different nitrogen species on carbon. You can see we have pyridinic nitrogen, amide nitrogen, pyrrolic, quaternary nitrogen. Now, what we see here is that the distribution of nitrogen species, we have always a distribution, is temperature dependent. You can see it's very different for the system less active and for the system more active, but it does not depend on the method of introducing the nitrogen species. For example, it's very similar for post-functionalized nitrogen post-functionalization or a direct introduction of nitrogen species during the synthesis by CVD, which is what you see here in this side, which you see here. So the nitrogen distribution is temperature dependent. And of course, the question is, a very long-standing question is, which nitrogen is the relevant species? Because in all the application we have explored, we see that the nitrogen functionalization at high temperature with this distribution of nitrogen species here is beneficial. But here we have different type of nitrogen. Is it the pyridinic nitrogen, the pyrrolic nitrogen, or the quaternary nitrogen? Now, as I show you, it is not possible to introduce selectively one nitrogen species by the different method we have explored. So maybe by thermal annealing, we can achieve that. And here, this is a temperature dependent study. Basically, we anneal, we thermally treat the starting nitrogen functionalized carbon nanotube, and we see whether we can maximize the abundance of one species. What you can see here is that, of course, all the nitrogen species go down, but at higher temperature, we can increase the abundance of quaternary nitrogen and remove the pyridinic nitrogen. Now, with these two systems, we can see whether there is a direct coordination between the metal center and the nitrogen. But XPS is not the right method to do that, because here you would see a shift. And of course, the shift within this very broad peak will be difficult to evaluate. However, absorption spectroscopy at the nitrogen K edge, so from the 1s to the LUMO, lowest unoccupied molecular orbital, will be the best method to identify meta-support interaction. Here you can see again that the starting materials has a resonance for pyridinic, for NH groups, and for quaternary nitrogen. And by the way, the nature of this quaternary nitrogen is still under debate. Anyway, we can see that the thermally annealed system, the resonance of the quaternary nitrogen is higher for the thermally annealed system. So what happens when we put nitrogen? So palladium. So as you can see here, the resonance of the pyridinic nitrogen and the quaternary nitrogen goes down upon immobilization of palladium. This is consistent with the direct coordination of palladium to nitrogen according to the Bly-Holder model, in which the sigma donation of the lone pair goes into palladium unoccupied state, and then we have a back donation from the occupied palladium orbitals into the unoccupied of the state of nitrogen. And this, of course, will reduce the transition matrix element for the lowest unoccupied orbital, consequently the transition probability, and also the spectral intensity. So this is how we interpret this. But however, we also see a broadening when we normalize for the maximum peak. We see also broadening. This is consistent with a charged nitrogen species and charge transfer from the nitrogen to the palladium. Now, the same effect is visible in the quaternary nitrogen. So we can confirm a strong interaction, if you want, between nitrogen and palladium. What is we have explored what this means in terms of reactivity, and here I'm showing, for example, the reactivity data of these materials in the oxygen reduction reaction. Here the long-standing question is, what is the role of the different nitrogen species, and particularly the quaternary nitrogen? Now, here you can see in red and in black, the black is the starting carbon nanotube with both type of nitrogen, and here is the red one is the annealed one. We can see that the onset potential is the same. We have 4 electron transfer reaction, which is what we want, with an increasing current density for the annealed one, which implies a better electron transfer, if you want. When we have palladium on the NCN, on this black one, we see a shift of the onset potential towards higher value, which means a lower over potential, which is good, and still predominant for electron transfer. However, when the quaternary nitrogen is occupied by palladium, we can see that the nitrogen species are not anymore involved in the activation of oxygen. And we see a 2-electron transfer to H2O2 typical of palladium. So here we could have shown really the role of the different species in this application. Now, I have said before that the carbon, so the nitrogen functionalities can directly coordinate palladium, and this can be seen spectroscopically. There is another example I want to show you in which we show the impact of the surface chemistry of carbon in stabilizing the metal nanoparticles of a given size. Now, this is the same system I showed before, the very active and the nitrogen, pyridinic nitrogen abundant and poorly pyridinic nitrogen content. And you can see here that this system are suffering fast deactivation because the reaction goes from a 2-electron transfer to a selective oxidation of hydrogen to H2O2 rapidly to produce water, which is unwanted. However, the PD473 is always unselective, but the PD873, there is a region in which is selective. Now, we have been looking at this by ex situ spectroscopy, because these are very challenging experiments to carry out in situ, particularly for XPS. At the moment, it's not really possible to do that. But already we get a lot of information, for example, by looking at the XPS in ex situ fashion. So here you can see the palladium 3D of the fresh material which describe nanoparticles with palladium 3D shift typical of palladium 0 for smaller particles, a palladium delta plus which describe the interfacial palladium with respect to the carbon, and also the PVA overlayer. Or any carbon overlayer on top of the palladium, and then palladium 2+, which are isolated iron palladium atoms, which normally are inactive for this reaction. Now you can see that at 12 minutes we see a bulk palladium formation, so we have sintering, and we also see some leaching, so which are detrimental, but we still see that this interfacial palladium is preserved even after 180 minutes of reaction. The same it's not the same for the not selective system. Here you can see, we see completely loss of this interfacial species, a main sintering and also leaching. So excessive exposure of palladium is detrimental, with the palladium undergoing leaching and redisposition on the carbon support as isolated species. However, on this more hydrophobic surface of the PD87 these nanoparticles and the overlayer are preserved. And this is this is how the way to control the selectivity. Now, learning from this, we thought, well, maybe we need to improve the stability of this material. We would need a more flexible carbon structure with a lot of nitrogen species. So the immediate idea came to use carbon nitrides because they actually offer exactly this characteristic, and we could see really an enhancement of the selectivity for a longer time. You can see here the difference between the most selective palladium on carbon nanotube and the palladium on carbon nitride. Of course, you see that the particle undergoes sintering, but they are still encapsulated, and the metallic palladium, which is needed for activating hydrogen and oxidizing it, is available, but still a lot of carbon overlayer that prevent the excessive exposure and leads to the selective formation of H2O2. So we continue. Another example of tailoring the reactivity of metal species on carbon is the following here, in collaboration with the group of Regina Palkovic in Germany, Aachen. We studied iridium on a covalent organic framework containing nitrogen species, particularly for the decomposition of formic acid, or the opposite reaction. And what we saw here is, for example, that in this case, we don't see anymore that Bly-Holder mechanism of interaction that I showed you before, because the poor aromatic character, if you want, of this material. But we still see a coordination, a sigma donation from the nitrogen to the iridium, as shown by this shift and broadening of the peak, with slight increase of intensity consistent with a donation from the nitrogen to the iridium, which is increased further when under hydrogen and the formation of metallic nanoparticles. So the withdrawing effect from the iridium metallic nanoparticles is even stronger. So obviously the stabilization effect of this covalent organic framework is rather encapsulating the nanoparticle and preventing further sintering, rather than a strong meta support interaction. So in summary for this part, I could show you with several examples that nitrogen allows tunability of catalytic performance at the nanoscale by acting as local site for anchoring metal through the hydrophilic character, through the control of reactants high availability. Because the overlayer and stabilization of overlayer and accommodation of the nanoparticle at the surface prevent the excessive exposure of metal nanoparticles. And of course, it's a dynamic interface. I'll show you the carbon nitride that that kind of encapsulation of the carbon in this matrix prevented the excessive palladium exposure and preserved the selectivity. The next example I would like to show you is on the electrocatalytic CO2 reduction, and now I think this is a very well-known topic and very crowded area of research, it consists on the reduction of the CO2 at the cathode side of an electrochemical cell using protons and electron produced at the anode side. Now the question is how we can make this reaction selective towards just one of CO2 reduction product, and particularly suppressing the parasitic hydrogen evolution reaction from water. Now, the next example is really application of operando spectroscopy to study this reaction, and particularly ambient pressure XPS. This is really this is basically an in situ XPS, which could be realized by reducing the path of electrons in the high pressure chamber using a small orifice where the electron escaping from the surface can go through and enter a differential pumping stage and being analyzed in the vacuum condition necessary to be analyzed. Now, this technique is quite established for studying the solid gas interface, but for the liquid solid interface, of course, this is even a bigger challenge. This research on trying to develop approaches to look at humidified interface or liquid solid interface started very early, and I think around 2010, there were several approaches at different synchrotrons to try to study electrocatalysis in situ. Now, one of the first approach was the one which we proposed using, it comes down basically to the design of the electrochemical cell. Now, this approach, which we have developed at Bessie, it consists on having this cell with the flow, with the liquid electrolyte flowing on one side, where counter electrode and reference electrode are immersed, and sealed using a polymeric electrolyte membrane, which act both as a sealing system and as provider of protons. And with this reaction, and it's possible to basically investigate many reactions of relevance in electrocatalysis. So the cell is then placed within the XPS chamber and generate a pressure in the millibar range. So we are far from the liquid phase condition. Other similar approach was suggested back then in 2010 at SLAC in Stanford, or for example, the deep and pull approach was proposed at ALS. Nowadays, worldwide, there is an approach available to study this at every synchrotron, as well as lab-based machines. And if you want to know more, you can have a look at this review. I'm not going to go into the details, but just saying that, of course, there are advantages and disadvantages of using one method or the other, and this has to be tailored towards the materials to be investigated. Now, back to the iron, nitrogen, carbon system for CO2 electroreduction, it's a really crowded area and has attracted a lot of attention, as you can see here. And one of the nice example was provided by Cosentine, in the group of Cosentine, where they show that homogeneous system like iron IM system could activate and reduce CO2 to CO. With the suggested mechanism that you can see here, with the nitrogen activating CO2 and water facilitating the activation of CO2, water coordinates through the iron site, facilitating the bending of the CO2. But what they show of interest is that by changing the functionalities around this iron IM, there was a possibility to enhance the CO2 reduction and thus these functionalities were acting as a local proton source. Of course, now you can think of that carbon materials offer opportunity for biomimetic design and really achieving a lot of functionalities around the carbon support, which could produce biomimetic approaches. Of course, due to the heterogeneity of the system, it's very difficult to characterize them. Now, what I'm going to show you is an example which we have been looking at this iron, nitrogen, and carbon system, where the carbon was a carbon support, like carbon nanotube, activated carbon. And we always found that in the CO2 electroreduction in both gas phase or liquid phase, the nitrogen functionalization at 873 K, or high temperature, basically, in which we stabilize all the nitrogen species I showed you before, we have a beneficial effect, and particularly we see carbon-carbon coupling chemistry. Now, the example I'm showing you is a system which has been synthesized following similar top-down approaches, so impregnation of iron, but now we use a graphitic carbon paper because this can be easily assembled on the in situ cell. So this is a material produced with the scope of doing in situ spectroscopy. And you can see here, by impregnation, difficult to control the nuclearity. We see a single iron atom here, chains at the edge, and larger particles. And the structure we observe here by EXAFS is a ferrihydride. So iron oxyhydroxide with iron in both the tihedric coordination, iron 3+. Now, we could confirm with this system, without going too much into the details of the catalytic data, that the nitrogen-containing system in a short range of potential is selective toward the carbon-carbon coupling you can see here. However, However, the system suffers selectivity, poor selectivity with higher with more negative potential, and but the oxygen containing system, oxygen functionalized carbon, actually is always selective toward hydrogen. You can see that, and it's only forming C1 chemistry here. But all very low Faraday efficiency. We look into this system in the gas phase CO2 reduction, and again, the nitrogen containing system is selective towards isopropanol, whereas the oxygen containing system is mainly methanol, and less active, if you want. Now, we could a DFT model analysis shows that is it correct to based on the TM picture that we see here. You see these iron atoms deposited on the graphite support. The DFT analysis showed that it is possible to think about a stronger interaction between the nitrogen and the iron species. And here, by doing XPS, I show you that I said before that, of course, looking at N1S and the iron metal coordination is very difficult because it's actually, the peak is broad and it overlaps with other species. But what we show here is, for example, that when we anneal these materials, with the pyridinic nitrogen's intensity increases and this shows that part of it was previously coordinated to iron, and by annealing we have freed it from the nitrogen species. So to a certain extent we could confirm the coordination. Now, going back to the dynamics under CO2 reduction, using the cell I have shown you before, this experiment were carried out at Bessie. What we have seen is that we look at the C1S. Obviously, we look at all the elements, but here I'm showing you the C1S. And you can see, so the analysis of the CR1S is extremely complicated, but we had the advantage that in Berlin at the Fritz Haber Institute, they had developed a very detailed fitting model by producing a lot of reference for carbon materials. And now what we look at is how the C1S change when we go above in the region of the capacitance region of the CV. So before the onset of CO2 reduction at minus 0.3 volt, and after, so when at the CO2 reduction onset, so when CO2 start to reduce. And what we see here is, of course, we have a dynamics of the different carbon species. We can identify single vacancy, graphitic carbon here in red, and then the edges, sp2, sp3 species, and amorphous carbon as well goes into this region here. And then we have the carbon oxygen species at higher binding energy. Now, there is some kind of restructuring of the species as one would expect because of the polarization. But what is interesting is that under CO2 reduction reaction, we see the formation of this additional component, which was found for as being as an atomic carbon in iron. So this is interesting because this was only found for the iron nitrogen system, and we could correlate with the in situ data of the mass spectrometry that shows the formation of isopropanol. So basically we could find this correlation. We further investigate other system characteristic of C1 chemistry, and we could not find the species. Now the question was, is it related to the CO2 and the CO2 conversion and the polarization, or we can form the species, for example, in other circumstances? So we did an in situ annealing experiment of the same system, and you can see here a different, these are a different kinetic energy. Sorry, I forgot to mention which one. So one is more surface sensitive and the other one is more bulk sensitive. And what we can see is that when we increase the temperature, we don't see significant changes. So the structure of the graphite is actually stabilized, and all the dynamics are observed under polarization condition. And particularly the atomic carbon was characteristic of CO2 reduction, electrical reduction condition. Of course, we have suggested the role of carbon similar to the role of the interstitial carbon in nitrogenase, which guarantee a iron-iron distance such that the carbon-carbon coupling of two adjacent carbon monoxide can happen, so the right distance for that. However, this is obviously will need to be supported by the other methods. Now, in this system that I have shown you, unfortunately, we have a large distribution of iron species. We had the bulk iron oxide hydroxide we found being they don't change upon polarization, so we can exclude that component. But then we still have the chain at the edges, and we still have the single side. So which kind of iron species is relevant? So that was the next question. So we have tried to prepare a more selective system by using now graphene, commercial few layer graphene, and immobilizing iron by iron exchange. So it's still a top down and hoping to exploit the defectivity of this graphene. In reality, you can see, for example, that again, there is a high loading of iron, more than I expected, but it's mainly decorating the edges, so in plane defects are not present at the beginning. However, when we start to anneal, and then we studied the thermal annealing process, because normally what we do is we impregnate iron and then we thermal anneal to stabilize a given structure. And here, as you can see, at some point we can see the migration of iron atoms inside the plane and the formation of isolated iron atom. Now I'm going to show you some videos of this, what is happening in situ. Of course, ideally, we would like to do this in liquid phase, but that's very difficult nowadays to realize in the electron microscopy. So the idea is to make some correlations by using this as a fingerprinting strategy. Now, as you can see, I show, if you look at this side, you will see that at some point they will start to, the iron atom will start to migrate. They are very mobile, and then we start to form isolated iron atoms. You see here, this particular here, and this particular here, and then also here. Right, and this was between 300 and 700. Now, if we stay at 700, you can see here these iron atoms, so they are very mobile, but at some point we form also dinuclear species. And this for us was very interesting because of course, the dinuclear iron site could explain carbon-carbon coupling. So, but you can see actually now it's very, very dynamic, but there are a lot of iron atoms here and also dinuclear species. And you could see also, if I run it again, that somehow there is a carbon, the graphite break, and there is a breaking bonding formation, and the iron move from the edges toward the in-plane position. Yeah, and they are very mobile, and at some point, even dinuclear species form. So one could imagine. Here you can see better how the graphitic edges are actually etched at 800 degrees C already, for example, and this will lead finally to the sintering of the metal, of the iron species into metal particles. Okay, so if we look now at this picture and we try to figure out which kind of iron ensemble we have, we can see the single vacancy with iron in the middle, the di vacancy here, and also this dinuclear species with iron-iron distance of 3.4 as determined by this TM picture. So we could also check for the nitrogen using yields, and here you can see a very complex actually iron ensemble at the edge of these graphene layers. And if you go through here and we look at the nitrogen abundance or the carbon, nitrogen, iron abundance, we can see how it changes from here to here. And then here this coincide with this, so we can see, for example, that there are at this point here where the bright area are, we see both iron and nitrogen. The ratio between them is for the total area is 5.36, so we have more nitrogen than iron if we consider this 1:4 ratio of this iron N4 site. In terms of nature of this of nitrogen species, again, very difficult to say because we see pyridinic, pyrrolic, and quaternary nitrogen, and the question is if it's a pyrrolic nitrogen or a pyridinic nitrogen. I will show you later that in our results are more towards indicating towards pyridinic ensemble rather than any pyrrolic nitrogen. Now we look at this materials in situ, and now I'm showing more the some kind of work in progress and where we are and where we need to be. These materials here were tested. We could confirm situ chemistry in the liquid phase with the nitrogen functionalized here indicated as NFLG, more active than the FLG. The good news is that we could confirm that the ammonia functionalization is beneficial. The bad news in a way is that no matter what you do and where you find your system, nitrogen will always be in commercial carbon materials. So even the FLG later show that there is nitrogen, as you can see here. This is the nitrogen K edge, but it's a different nitrogen with respect to the nitrogen we introduce. So what we see is that initially we have some kind of conjugated nitrogen, and when with the ammonia treatments we introduce additional isolated still pyridinic nitrogen. Now if we compare with the iron phthalocyanine here, or porphyrin, sorry, we can see that it's really different from the system. It is slightly different, particularly in this area here. Is different from, so it is not a pyrrolic nitrogen we have. The EXAFS analysis at the open circuit potential, so during in situ experiment, for these two systems is very different. And also the nitrogen speciation here of the starting material is different, as well as the carbon speciation. So what happens in situ? We see a slight change from open circuit potential, and increase in the coordination number in the first coordination shell, and some changes in the second coordination shell, but these are minimal for the FLG system, and this is consistent with what the people found in literature on this iron nitrogen 4 system. Now the NFLG, so the one in which we additionally put nitrogen, it's different and is more complex. You can see here that we see a change in the coordination number in the other direction, but under condition of CO2 reduction reaction, which is -2 volts in this case versus silver chloride, the system is not really very stable in a way, and the second coordination cell somehow shell growth. So understanding this is a challenge, and I will show you where we are. So first of all, we try to fit this to model this the starting point, the open circuit potential. And by the way, this data were obtained at B18 at Diamond Light Source using the cell in situ cell we have developed there. So if we look at this, we've applied force fields, so classical physics, electrostatic interaction to model this site with 4 pyridinic nitrogen. And you can see that in terms of distances, with first coordination shell and the carbon atom here, the next one here, this carbon atom here, described by this this signal here. In terms of distance, we are okay, but the intensity is not is much lower. If we remove the apical ligand, the intensity decreases, but still not as lower as the starting material, as the open circuit potential, as the experimental data, I mean. We have used DFT, and here are compared DFT with the previous model, and not big change, so we are still far. This is just to show you that basically the distances are very well described with this D vacancy site, but the intensity for heterogeneity in terms of the bond length. So then we look into see whether how a model with 4 pyridine compare with one that has pyrrolic, for example. Now the pyrrolic one is here, the green one, and you can see that it's completely different. Of course, this analysis is complicated by the fact that we can have different species undergoing leading to an EXAF signal more complicated than that. Looking at a single vacancy, iron in a single vacancy, of course, the force field approach gives interesting results in terms of coordination that, from my perspective, are not what I would expect, but the relevance of this data are on the fact that actually we can see still what happens if in terms of the relative intensity between the first coordination, so the direct bond here, and the other carbon atoms around. And you can see that for a single vacancy, you would expect this peak a little bit higher, which does not fit with our experimental data. So the relative intensity, so we can exclude that we have this type of species. We look also into the dimers, and particularly we look into the dimers for the in situ data, which could, because we think that they can be formed after, as we saw during the thermal annealing, the voltage could have a similar effect. And here we can see, for example, that this distance here could be possibly described by this iron dinuclear site. Anyway, we also try to see whether by changing arbitrarily the distance, because this will clearly show that we need maybe a more advanced approach towards this analysis, because you can see here that the starting material at open circuit potential can be described mainly by this wine iron site in the vacancies, more or less, but not completely, and particularly not completely at this higher distance. And this higher distance actually increases upon CO2 reduction. So we are trying to see what is happening by changing the distance slightly of this nuclear site, and see whether we can fit the spectrum by a combination of these two, for example. We are also looking at studying this. This is a static simulation in which we look at the interaction of this site with a layer of water containing KHCO3 and CO2, of course, and we see some kind of distortion of this iron atom, but we would like to study this more dynamically, and maybe this kind of study by MD simulation, and maybe this kind of study can fit into the models that we can use to fit the data. So as I say, this is a work in progress. and quite challenging, probably also the requirements of machine learning approach to change, to see how the EXAFS signal change with changing the distance of this iron, nitrogen, or carbon atoms. With this, I would like to conclude. I would like to acknowledge my team at Salford, my long-standing collaborators, the Fritz Haber Institute and at Bessie, in the University of Messina, of course, at Diamond, Diego particularly, who is helping with trying to find an approach towards analyzing this data in a more advanced way, including the dynamics and of course, the Catalysis Hub, Lofty, and Professor Richard Cutler for support with computational approaches. And of course, thank you for your attention.
Thank you very much, Rosa, for a really fascinating and very comprehensive talk. We've had some questions come in already, and I'll read them out. If you have any questions, please type them in the Q&A. So there's a couple of questions come in on the SACs, which is the best method to repair gram scale SACs.
Yeah, that's so. Of course, the best way to prepare them is not the one I have shown you, because as I show you, the top-down approaches, they lead, even with ionic exchange, which in principle should only allow the interaction of iron with defect sites. As you can see, as the graphene layer are populated by iron atoms, and that was really like just wetting in the solution and taking out, washing and removing the not strongly interacting species. So that is not even a good method. I think the best is to go from, for example, metal organic frameworks and doing some thermal annealing, if that is advantageous in terms of energy input. However, that type of methods have the problem that some of the metals are not exposed. So, but at least for fundamental study, probably they are the best methods to study the effect of the iron species the way I do. However, there is something that I haven't presented is a recent work we have done using biomass derived carbon, and in which we show, for example, that the orange peel has a chemical composition such that allows all this, because the carbon matrix has a lot of roles, not only stabilizing the iron, but also, you know, protecting the species from sintering and so on, and the complexity enabled by the biomass could be exploited. The chemical complexity of biomass could be exploited. For example, we show that the orange peel contains a lot of organic species that are actually beneficial for the reduction of CO2 to formic acid. So yes, you know, from a real scaling up, I would go for biomass derived carbon.
And then sort of the related question is, how do you choose the metal precursor and method? Which you sort of answered.
Yes. So how I use it. I used initially we used iron nitride, but was not a good choice. Iron chloride we tend to exclude, although because the chlorine has an impact on the reactivity for CO2 reduction. So in reality, that one would be an additional element of complexity, because it has a beneficial effect as well. I have used more salt, is iron ammonium sulfate, because this has iron 2 plus, and you know that iron 2 plus is more stable as a single species, as a single as a monatomic complex in aqueous solution, a little bit higher higher stability than iron 3 plus. So this is how I chose to prevent the precipitation of iron. This is the choice, you know. You want to have the ion exchange with the surface and not the precipitation of the iron oxyhydroxide in the bulk of the solution and then the deposition. And if you do that, you can control the speciation. But of course, one has to know exactly the chemistry of the carbon to do that. But this is how the rational, right? You would like to control the interaction of the metal species with the carbon support and prevent precipitation in the bulk of the solution.
Okay, thank you. And then another question is, how are you converting nanoparticles to single atoms? I think this came in during the talk.
I'm not so sure.
Is it just that you get single atoms from your synthesis method?
Yes, you get a distribution. That's the problem. You get particles and also single atom, because they tend to form during the thermal annealing. I show you this video. So yeah. Before we have this iron species decorating the edges, and when we look at the EXAFS analysis, they look really like similar coordination as ferrihydrides, so they are coordinated, they are chain. But then during the thermal annealing, you see they move towards the in plane. Some sinter as metal. I didn't show you that, but we have also metal nanoparticles sometimes at certain temperature. Basically, when the graphene start to etch a lot, but they do form during the thermal annealing.
So we've had another question has come in regarding the deconvolution of the C1s spectrum and the presence of the peak related to defects at the lower EV than the CSP2. How are these species formed, during the thermal reduction of metal carbon composites? Could it happen that the reduction of the metal causes the oxidation of carbon and the release of CO and CO2, giving rise to defects?
Wow, that was long.
Yeah.
Right, in terms of the presence of these defects, yeah. So our idea is that the formation of these dye vacancies are facilitated by the presence of the heteroatom, for example, the iron. How do we know that this is single vacancies? Because they have done a lot of study on sputtering graphite HOPG with argon, and these sites start to form, and then as the holes become bigger and bigger and bigger, then they see actually a shift from the lower binding energy side with respect to the graphite to higher binding energy side. So this kind of investigation were extensively done to prove the shift. Now, in why they exist under this condition, so we see that they are there already, because we see these iron atoms in the vacancy, and we assume that these are those species, and yeah. And the second part was about?
Could it happen that the reduction of the metal causes oxidation of the carbon, release of CO and CO2, giving rise to defects? This is during the thermal reduction of the metal carbon composites.
So the reduction of the metal caused the oxidation of carbon. I would not, I mean, so the immediate things that I would say is that the reduction of the metal happens during the thermal annealing and water is dissolved. I don't see why the CO2, the carbon should be oxidized. Yeah, I don't think this could happen in the low pressure condition that we have. But definitely any sort of oxygen species on the carbon will also be reduced. But the metal oxidize the carbon before and then CO2 is released, I'm not so sure.
Okay, so we've got a couple of questions that are fairly similar, and I think it's asking, in the in situ characterization metals, what characterization are you using to distinguish the different vacancies? You said that it's been extensively studied, but how? I think people are asking.
Yes, so for this one, I would like to address you to refer to the paper published by Raoul Bloom. He's the expert at the Fritz Haber Institute, and he studied a lot of materials. It's a paper in ChemCatChem. I don't know if I'm able to find it, but in if you look at my RCS paper in which I have presented, in which these data are reported, there I have a reference to this paper here, and basically it's really long-standing research. I was there, and I think it was a 10-year-long research on all the different type of carbon materials, from carbon nanotube, different type of carbon nanotube from different supplier, different treatment, oxidations, and thermal annealing, and also HOG and sputtering with argon or with to introduce defectivity. So and this comprehensive study has led to this fitting.
Okay, so if you have time, there's one final question, I think. How did the palladium binding energies change as the nitrogen environment changed with annealing for the palladium and nitrogen carbon nanotubes, e.g., did the loss of the pyridinic nitrogen species lead to change in palladium binding energies?
Yes, so the pyridinic nitrogen, according to my observation, when it is coordinated to palladium, shift to higher energy and assume a similar energy to what is reported, like for CN groups, for example. This is why I say it's very difficult to distinguish. And of course, after the sintering or thermal annealing, the pyridinic nitrogen goes back to the original binding energy. And we could also see the same behavior in the case of the iron, for example.
Okay, interesting. Well, Rosa, thank you very much for a really excellent talk. I think the sheer volume of questions shows how interesting it was.